Okay, welcome to our presentation on contact-free simultaneous sensing of human heart rate and canine breathing rate for animal-assisted interactions. My name is Timothy Holder, and today I'm presenting with Mushfiqur, Rahman. Next slide. In this presentation, we're going to give you a brief introduction to our work and to the canine-assisted interaction space. Then we're going to talk about how we approach remote breath rate estimation and heart rate estimation. And then we're going to discuss our frequency estimation results before concluding the presentation. Next slide. All right, let's get started. So animal-assisted interactions are complementary treatments. They use animals as therapeutic agents. A subsection of animal-assisted interactions are canine-assisted interactions, and they employ dogs. And they also aim to improve quality of life, just like all the other AAIs. And in the research, they have been shown to have neutral or positive effects for either subject involved. Work in the canine-assisted interaction space also extends to other forms of working dogs, as well as companion or pet animals. Next slide. So within the canine-assisted interaction or CAI space, there are 5 macro sources of data. The first is environmental data, and that can come from ambient temperature or relative humidity. There's contextual information, for example, having an individual play session outside or a group therapy talk session inside with an animal. And then there are 3 individual sources of information: the psychology of either subject, the behavior of a subject, or the physiological responses of a subject. From within these various information sources, the current canine-assisted interaction literature tends to report subjective and qualitative data information, among other things. There have been some attempts using wearable devices, implantable devices, and other systems to address these gaps in the canine-assisted interaction literature, but some of these solutions tend to be obtrusive to the interaction, uncomfortable for one or both participants, and they also tend to focus on only one of the 2 interactants. Next slide, please. And so we started to investigate the concept in the area of contact-free physiological sensing. Briefly, on the animal side, there's been some work done on detecting respiratory rate as well as skin temperature using RGB cameras as well as infrared cameras. On the human side, there's been some work detecting heart rate, blood oxygenation, and some other signals in stationary humans or individual body parts. And so we are investigating the question, can we do contact-free physiological sensing in a dyadic canine-assisted interaction context? Next slide. And so our experimental procedure involves many things. In the top right, you see that we're using roughly 2 to 3 reference devices of each subject. So on the human, we have 3 reference devices that are collecting together electrocardiograph and inertial measurement unit, which is a measurement of activity. And then on the dog, we have 2 devices, one on the chest region and then one on the neck region that is also collecting together ECG information for heart rate and IMU information for activity. The entire research space is supported by 1 or more cameras. The main camera is a commercially available camera from laptop webcam, and then we have 2 auxiliary cameras from smartphones as well. So the procedure is to bring 1 human subject or 1 canine subject into the research space to affix the reference devices and set up the various cameras to give them a short break, which is what's represented by the black arrow, and then proceed with a calm human-canine interaction before another short break and removal of the various systems. Next slide, please. And now my partner, Mushfiqur, will talk about the remote breath rate estimation.
Thank you, Timothy. In this slide, we will see how camera-based dog breath rate estimation can work. So there are 2 types of method of dog breath rate estimation. The first one is contact-based method, and the second one is contactless method. So when a dog takes breath, then there is a visible up-down motion in the dog's lungs and diaphragm region. So in the contact-based method, generally a wearable devices such as a dog harness is put on the dog's body, and so it can record the impedance that is caused by the breathing, and hence as the impedance changes with time, it can just analyze the signal of this impedance and get the breathing rate. In this experiment, we are interested in the contactless method using a digital camera. So this digital camera records the video that contains the visual motion of this region as video data. And in the later step, we will see that we can use processing algorithms to to extract the breathing motion of this region and get the breathing rate. So after recording the video, at the first step, we draw a rectangular bounding box on our region of interest. So this region contains the motion information that is caused by the dog breathing. So we focus only inside the bounding boxes pixels, and because only these pixels corresponds to the breath motions. Again, as we select a bounding box at the first frame of the video, but as we move forward in the video, the frame at t is equal I will not be the same as the frame is t is equal 0. So the positioning of the region of interest will change. And so we need to update the positions of the pixels. And so we use a optical flow algorithm that is reliable to get the differences of these frames and get the motion vectors for each pixels from one frame to another frame. So we use GMA optical flow algorithm to compare from the first frame with the new every frame that occurs in the video. And so we update the our region of interest that changes over time. So after that, after that, we need to get a signal that contains the signature of dog's breathing. For example, if we see this video, we can see that in this region, there is some kind of motion, and you can see that the dog breathing has one kind of reflectance on the visual motion in this region. And so we need to get one kind of signal that contains the signature of dog's breathing. So as we have already selected the region of interest, we can just get the spatial averaging of our selected pixel locations, and so the noises are decreased, and so we can keep this displacement signal as our estimation of our breathing signal. But obviously, this signal also contains the information about other kinds of motions, but overall this displacement signal has the trace of dog's breathing. So in this slide we will see how we can process the original displacement signal to extract the more visible dog's breathing signal. So first we do a detrending by using a window of 2 seconds. Then we can see the plot becomes more visible, and here we can see a periodic motion of this kind of signal that is actually more relevant to the dog's breathing. But still we have some kind of very high motions here, and this actually does not correspond to dog breathing, but to other kind of motions. So we again compensate the large motions and get this kind of nice graph where these periodic small motions corresponds to dog breathing. So as similar to the breath rate estimation, we can also camera-based heart rate estimation. So in this case, also we can compare with the camera-based method with the contactless method. In the contact-based method, we generally use a device such as PPG device, and so we have two way of this device. One in this one side, it actually passes light by a light source, and the light passes through the human finger, and this is actually detected by the optical detector on the other side. So this device actually measures the absorption of light inside this human finger. And as a fact, we know that the absorption actually depends on the percentage of oxygen in blood, and percentage of blood depends on how the heart pumps oxygen. So this is the signal that corresponds to some kind of heart rate information, and we can analyze this signal to get the heart rate. But in the camera-based method, that is contactless, and that actually depends on environmental light, and it records the brightness of the human skin. Here we can use the fact that reflectivity also changes with the percentage of oxygen in the blood, and so heart pulses heart pulses oxygen to the blood. And so if we use a digital camera to get the brightness, we will see a sinusoidal like curve in the brightness of this region. So this is the information that we can process to detect the heart rate. So as similar to the breathing rate estimation, here we also make our task a lot easier by selecting a rectangular bounding box in the human skin. So we can draw this skin on human hand or human face or human leg. So we only focus on the brightness or motions of this region, and so we can use the change of the brightness in this region. So again, a human can change the position of the skin, for example, hand or other skin regions. And so we need again a optical flow algorithm to estimate the motion vectors for each pixels for our initial time frame and any arbitrary time frame I. And so we do the GMA optical flow algorithm and update the region of interest for each new frame of this video. And then again, we need some kind of signal that actually has the correspondence of our human heart rate. And so here we make use of this fact that the brightness changes with the human heart rate, and so we do the spatial averaging of the brightness for all of the three color channels, red, green, and blue, and we keep these signals as these signals has the signature of human heart rate. In this slide, we will see how we can process the general intensity signals that has a kind of a signature of our heart rate, and we can increase the signal to noise ratio of the signal. So first, we do a linear combination of all of the three channels, and hence the signal quality gets improved, and we have a signal of one channel. Then we do detrending using a signal of 2 seconds window, and then we get a more robust signal. And then again, this signal can also contain some kind of variation due to angle changes and also change of the brightness of the environment. And so we discard the very large changes and keep only the variation that is periodic and that is small in nature. So as we have the time domain signals that has the signature of either breath rate or heart rate, now we can use the frequency domain analysis. So in the frequency domain analysis, for example, here we have chosen a signal of 5-second signal and plotted the power spectrogram density of that signal. So we can see that multiple frequencies have a peak here, and so we cannot be sure which one correspond to our desired frequency of heart rate or breath rate. So what we need to do, we need to build a spectrogram by stacking the power spectrogram density for each time frame that is continuous. So if we do that, we get this kind of a spectrogram, and these traces that are the candidates for the trace of human heart rate or breath rate. But still, we need another kind of work, because the traces should be temporally smooth, because heart rate or breath rate does not change instantaneously. So we need to take this into account, and we have to use a robust frequency estimation algorithm to get the traces from this spectrogram. Here we show the results and compare with the ground truth for two videos. This first one is for breath rate estimation, and we can see that the red line that corresponds to our camera estimated result, and the blue line that corresponds to the ground truth or gold standard measurement. And so we can see that the result follows the gold standard devices result, with having a mean relative error rate of 6.4% and a root mean square error of 2.9 breath per minute. So for heart rate measurement, we can see that in this case, we have a mean relative error rate of 5.1% and a root mean square error of 5.2 breath per minute for this video. In this slide, we summarize the results of all of the videos as the mean of all of the videos that we have collected and tested our algorithm on. So we can see that we have used three metrics: root mean square error, standard deviation of error, and mean relative error rate. And so we can see that for breath rate estimation, we have RMSE of 6.9 BPM, standard deviation of error of 4.1 BPM, and mean relative error rate of 6.5%. For heart rate estimation, we have RMSE of 6.1 BPM, standard deviation of error of 4.7 BPM, and mean relative error rate of 9.7%. So in these two tables, we tabulate how our performance varies with the setting of our experiment. For example, when we turn off clipping or when we turn off detrending, how the performance varies. So we see that these our steps like standardization and detrending, those have effect on the performance. Furthermore, we test the robustness of our method explicitly by testing on a scenario where the visual motion have two types of motion. The first one is the motion due to the dog's patting. So the human is patting the dog with hand, and also the dog has the breath motion signals here. And so how our method works in this scenario where two kinds of motions are present. And so if we first use our algorithm at once, we can see that our method gives the most significant trace, that is the trace of frequency of patting at around 60 BPM. But again, we can just nullify or zero this trace, and again we run our algorithm on the remaining spectrogram, and this time we get the second most significant trace, and this trace corresponds to dog breath rate. So our algorithm is still workable when multiple types of motions are present. Now I will hand over to my partner, Timothy.
Thank you, Mushfiqur. In this presentation, we briefly introduced canine-assisted interaction as well as some of the gaps in the literature, specifically focused on some intrusiveness to the interactions, uncomfort or discomfort due to the devices and systems currently being used, as well as not focusing fully on both interactions. We also talked about our approach. We have a quite simple human-canine interaction protocol, and we're using several reference devices on the human and on the dog, as well as commercially available cameras. And Mushfiqur went into detail about how we do the canine breath rate and human heart rate estimation, as well as how our results compare to the reference devices and the robustness of these methods. And so in this proof of concept work, we tried to address the question of can contact-free physiological sensing be used in a dyadic canine-assisted interaction context? And we think that the answer is yes. All right, and we're going to move on to the next slide. And so our next work in this space is going to be to include and increase the subject count, so including more subjects to investigate some additional signals, like for example, blood oxygenation, to consider extending to additional animals. And since the devices that we used in part of the study are commercially available, there's potential for extension to animal shelter work, various veterinary scenarios, as well as at-home citizen science use. Next slide, please. We would like to acknowledge funding from the NSF as well as IBM. And we'd like to thank Dr. Alpo Boskert, Dr. David Roberts, Dr. Chai-Wei Wang, and their research groups for research support in this work. Next slide, please. Thank you for listening to our presentation.